Put 100 excited atoms in a box, far apart from each other. Each one emits a photon independently at some random moment. The light builds up and fades over the typical atomic lifetime, coming out as an ordinary incoherent soup. The math here is linear. Because the emitters are independent, those 100 atoms simply produce 100 units of light. Now shrink the box so the atoms are closer than a wavelength of the light they're emitting. Something different happens. The atoms feel each other's electromagnetic fields through the vacuum and synchronize. When they emit together. 100 atoms cooperating produce a flash that's 10,000 times brighter than the same 100 atoms acting alone. In 1954, Robert Dicke published a paper titled Coherence in Spontaneous Radiation Processes. He pointed out that if two atoms are close enough that their emitted photon fields overlap, you can't treat them as independent emitters. Dicke's insight was that physical proximity and field overlap change how independent objects release energy. They enter a collective state where the emission dipoles lock in phase. Standard radiation theory says the rate of emission is proportional to the square of the transition dipole moment. For n independent atoms, you just add their contributions together. It's a linear progression. But when the atoms are in phase, the total dipole moment becomes a coherent sum. The total emission rate scales as the square of the number of atoms. You've gained an extra factor of n by forcing the dipoles to add coherently. The scaling is dramatic. For a coherent cloud of 1 million atoms, that's a trillion-fold increase in peak emission rate. There's a trade-off required by the conservation of energy. Because the collective dipole is larger, de-excitation happens n times faster. You get a pulse that's n squared times brighter, but it's over in a fraction of the time. Superradiance isn't a free energy cheat. It's a mechanism for compressing an existing energy budget into a brief and powerful flash. It took nearly 20 years to verify this experimentally. In 1973, researchers used hydrogen fluoride gas to record the first clean observation of superradiance. The experiment confirmed Dicke's prediction of a delayed burst. The atoms spend a dark period organizing before the flash, not emitting until the collective state has built up. Today, this physics is used in ultra-stable strontium clocks at Gila. These superradiant lasers produce line widths far narrower than any conventional cavity laser. Free electron lasers at SLAC and DESI use a related collective amplification to produce X-ray pulses billions of times brighter than any synchrotron. You'll find these collective states in dense plasma physics and quantum sensing. Black hole superradiance is a different mechanism named by analogy. Dicke's n-squared scaling law is a verified principle of physics utilized across modern quantum research. This scaling law is the foundation of Forbes' theory about the three MH370 orbs. He suggests the orbs generate a magnetic field effect much larger than any individual device could produce alone. If the three orbs operate as coherently coupled emitters, the total projected energy into a shared configuration scales as 9 times the single orb value, not 3 times. Since 3 squared equals 9, this perfectly applies the Dicke scaling law for 3 synchronized emitters. Even if the geometry can't reach full coherence, any degree of phase locking provides a multiplier that exceeds simple linear addition. The challenge is the physical scale. Atomic superradiance occurs at sub-wavelength distances, but these plasma orbs are meters apart. Standard plasma dynamics won't naturally phase lock over those distances. Achieving it would require active engineering, like a shared clock to keep the devices in sync. Forbes' 9 times multiplier claim is a direct application of the Dicke scaling law. The question is whether classified macro-scale plasma engineering currently exists to execute it.